So moving on this to phase 5 of the bond lab. So we're going to deal with string decoding here. So this is something that, if you've ever looked at a malicious binary, this is something that definitely I expect you to come across. And a very common example would be XOR decoding. So you take some random integer and you XOR each byte of the string with that value. It just masks the string so that when we're in IDA, we don't get something nice like "Welcome to my fiendish little bomb." You'll actually have something that isn't even recognized as a string, perhaps, or maybe it'll be recognized as a string, but it just looks like gibberish, and you just totally disregard it. Just a quick and easy way to hide things from you, make your job a little bit more difficult. Now, that being said, it's any string that the thing needs, that the application needs, it's going to at some point decrypt it. So either it's going to do it inline and you can just debug it and wait until it actually does the work for you, or you can trace down the function that actually decodes the string and figure out what's going wrong. So ASCII table is really handy. One of you has already got this open. So if you want to Google ASCII table, that would be one way of coming up with the translations of integers to bytes. Also, IDA allows you, characters. IDA does this translation for you, so you may come across a situation where you want to convert the decimal representation or the hex representation of a string or character into whatever that character may be. And we talked about that using the R key. So that might come in handy. And also bit masks. This is something that you're going to come across. Bit masks are often used for configurations. So you might have some bit mask that determines, you might want to have a configuration file that uses a very small amount of information. Maybe you're trying to, back in the day, use a floppy disk or use some small media, transfer your information. You have all these configuration settings for your application. Well, one of the easiest ways to store that information is a bit mask. The complicated thing is actually setting each one of those bits and knowing what the correct string representation or decimal representation of that bit mask is. But this is common code, and this is something you're going to see. You've got removing a pointer into EAX. And it's using this move SX instruction that says sign extend. Okay? So if the leftmost bit of this value located at EDX has a 0 on the farthest left bit, so that's the highest bit, then everything down to the byte, because we're doing a byte operation here. The first 24 bits are going to be set to 0. And if it's 1, then all those bits will be set to 1. And I can do a demonstration on the board if you'd like. But the next thing we do here, which kind of makes the whole point. Well, no, it doesn't make the whole point. We've got AND EAX 0F. So what are we going to be left with after this operation? The bottom 4 bits. Right. So regardless, even if we didn't do the sign extend, this 0F would wipe out the upper three nibbles of this, or the upper 3 bytes rather, of the 4-byte value stored in EAX. So we're going to end up with just the last 4 bits. So keep that in mind. Bit masks are going to be what you're going to come across. So back in main, this byte is going to affect the instruction where that's referenced. So instead of undefining it, I'm going to click on the 69 hex, hit R, and I see there is an I there. So the character representation of 69 hex is I. So now we have all the letters as giants. So has anybody figured out what I meant by half of the input is actually useful?
It looks like it's turning the bytes in the input string and offsets in that array, but it's only in the lower nibble.
Right, exactly. So you've got two nibbles and a byte, okay? So in this case, 0F. And same goes for all our input characters. And this is where a hex table or ASCII table comes in handy. So this byte array here, it has 16 characters. Okay, and I know this because it starts at something ending in 80 and goes up to 8F. So F is 15 plus the one at 0, 16. So each one of these corresponds to the values of the low nibble of each input character that we put in. So var C gets this value from DL, and we have to trace back up what's actually determines that. Yeah, EAX here is our offset into our byte array. And that comes from this AND EAX OF, which, as I mentioned before, is a bit masking instruction. I'll zoom in for those of you who are remotely working. So we keep working our way back up here. EAX is coming from this byte pointer EDX, and EDX is arg0 plus arg10. And we're in a loop. You should recognize this from before. This is our counter. Or as people use, or typically write in their code, I or index. So we're taking each character in our string, we're getting the low nibble, and then we're converting that using this table. So now we have to figure out, well, how do we spell giants using this? So this is my trusty notepad here. We see G is at offset F. T is at offset C. N is at offset B. So it's G, T. Working our way back up, we got A, which is at offset 5. S is at offset 1, and I is at 0. So now I'm going to use an ASCII table. And let's go to someplace I trust. Of course, I believe everything Wikipedia tells me. So this table could not be wrong. And so what I've got here in my ASCII table, I've got the low order nibble and the high order nibble. Okay, the high one we said doesn't really matter because that's being ANDed away. And the low order nibble right here, that's really what we're interested in. So, spell giants, we need F, O, 5, B, C, 1. And your answer can vary. It's not going to be this, as long as it has these in the lower nibble. So does anybody have a solution? Okay, what do you have?
I've got capital O, @ sign, capital E, capital K, capital M, capital A.
Okay, so all capitals except for that @ sign.
So I just went with the 4-0. Starting with 4-0.
Starting,
I started with 4-0 because it's the first one I saw.
right. Okay. So, just double check our work here. We've had capital O, table here. And we've got, so, and you can see that there's some rows that are more of a pain to use than others, special characters and whatnot. Obviously, we're probably not going to be using these first two rows, which are a whole bunch of control characters like null and ACK and bell and all these. So this 4 row, definitely a good row to use. Just got to make sure you're using all capitals. And we put that into our application. Move on to the next one. So, anybody have any questions about that? So, this is your old school kind of, we've got our Rosetta Stone here in our byte array. And that's telling us how we get to the promised land here, how we get our answer. So answers may vary. Once again, you don't have to use these exact ones because all that matters is the low nibble. But that's the end of that one. So, any questions from online? Okay, and Andrew's just saying you can use all lowercase letters, which is less key presses. You know, that's the way to do it. And, right. But that requires you to use 2 lines, so that is another way of doing it. All right. So we've made it to phase 6. So moving ahead here, we've gone through this stuff pretty quickly today. How's everybody feeling about it so far? Pretty good pace? Anybody have any particular questions about IDA thus far? No? Okay. Well. All right. This is the last thing we're going to do today. Got some material to discuss before we dive right into it. So this is where I'd spoken briefly this morning about coloring. Okay. At some point, you're going to get code that's so ugly that just trying to understand where you are in the code is going to be especially complicated. So there are a couple things that you can do within IDA to help you keep your code organized and to help delineate, what's what. Is anybody colorblind in here? Okay, so there are alternatives. I'm actually going to start out with an alternative to coloring. So, but before we do that, I'm going to discuss using structures, and unfortunately I have to zoom out a little bit here. So those of you following along online, I had to zoom out a little bit because not everything fits within our window here. We have the exact size on our image here, so we want to get that to fit in here properly. Just go ahead and click on the bottom left page 6, and we're on the Structures tab. So, who in here is familiar with structures? Kind of, sort of, well, not quite sure. Couple yeses. Okay. So when we have a bunch of related information, and essentially information that's not necessarily stored all as the same type, say we've got some strings and some integers mixed together, we got some characters, we're going to organize that information into something so that they can all be packaged together and used all in the same place. You might do this if you have a list that's dynamic. Okay, so you don't know how many elements it's going to need. You want to be able to add stuff on the fly, and you don't want to, at the beginning of the program, say, I need 1,000 elements. You might start out with 50 and only need 50, but then somebody else might need 10,000. And so do you always allocate 10,000 memory spaces for these things, or do you do it on demand? So on demand gives you the ability to scale up your application in memory and not necessarily use memory that's not waste memory by pre-allocating everything. So as you can see here, we've got structures window in IDA. It's talking about a list node. Structure definition looks something like this. Let's say we're defining a person. And structure has, first of all, you got to have a name. So say we have name, and we'll give you 128 characters to store that. Person also might have an age, stored as an integer, and so on and so forth. So you might have another person that you point to. So you might have a friend or something, or maybe you have a bunch of them. So when a program is compiled, this information is all stored contiguously. Okay. That is to say, so in this case, we've got a statically allocated string. Okay. So you'll have 128 characters at the beginning of this thing. And then you'll have an age, and that's 4 bytes. and then you'll have this pointer to a friend. So that's going to be, what do you think? Say we just have a pointer to a friend. Friend just being the name of this person. How many bytes do you think are used to store this thing?
4 on the 4 with this one.
Right. So just a pointer. The information about the friend is stored somewhere else. So somewhere else you'll have another person. That will have these same things. All right. So not all information about structures are necessarily stored all in the same place, but at least a pointer should be included in your structure, and it should be all stored contiguously in memory. So this will be stored at the lowest byte, lowest address, and this will be stored at the highest address. So in IDA, you'll see stuff like this right here, top. We've got var4, some local variable, we store it in the EAX. And then you'll see EAX plus 8 stored in the ETX. So we're storing the base of this structure into EAX, and then we're actually getting one of the members, which is stored at 8 bytes away from the beginning of this thing. So in our case here, we'd actually be partway into our name. So that would be the 9th character of our name. So in IDA, we have this ability to view structure offsets. And the first thing we have to do is to define a structure. So to give you a little leg up, in phase 6, we're going to make use of structure definitions. So let's go to our view, open subviews, structures, and you can get to the same thing by hitting Shift F9. All right. And so we've got some predefined structures in here. I'm just going to put my cursor at the top here, and I'm going to hit Insert. And we're going to add a list node. And these guys are going to contain 3 members, each 4 bytes.
What are you pressing? Sorry.
Sorry about that. So you press the D key. So we'll undefine all of these. Okay, so at the top here, we've got just a little reminder here for you. Insert and delete. So insert will create, and delete will delete the entire structure. So D, A, and asterisk are possibilities for adding structure members. D is going to give you a decimal, some sort of integer, or you can use that to store pointers. If you hit D once, it's going to give you a single byte variable. If you hit it twice, you're going to get a word, and 3 times it'll give you a double word. So create one of those just by clicking on list node, hitting that 3 times. Does everybody have field 0? Same place? Okay. Now that we've got field 0, click on the bottom list node just before where it says end S. And once again, hit D 3 times. going to give us field 4, and it should say DD question mark at the end. Once again, click on list node at the bottom, and we should have one more variable, field 8. And I'm going to give you that last one next. Okay. So, who can tell me what next is? Somebody back here?
Pointer. Pointer.
Okay. So in a list, the way you keep everything connected together is you can either have a singly linked list where you always have to know where the first one is and work your way to the end, or you can have a doubly linked list, which you could go forward, you could go backward. In that case, usually the list is circular. So the last one should, in a good implementation or a good usage of lists, the last next variable should contain the value 0, which, but you know, it is somewhat arbitrary. The trouble is that if you don't have some indicator of an address that you don't ever want to access, then you can't. You have to have some way of saying this is the end of the list. And generally, you're not going to use address 0. So because of that, by convention, we use 0 as the end of the list. So go back to our IDA view and go to phase 6. You'll see this ugly monstrosity, and I can zoom out a lot, and it's still not there. To zoom out really far to actually see the entire thing. Looks like a mess of spaghetti. You'll see actually in this block right here, you'll see what I was talking about earlier with a reference ECX plus 8. So everybody, can everybody find that block? It's from the farthest right. How about we'll take the farthest right block? All right. Starts out with this move EAX EBV plus bar 4. And then we have this move into ECX EAX plus 8. So if we click on this guy here, click on the EAX plus 8 anywhere in there, press T, and it gives us a bunch of potential offsets. So I'm going to choose list node.next. So this gives you some sort of context as to what is actually being used here. So what is this? What are we trying to store in ECX? Okay. Now, feel free to ask questions about structures as we go along. I'll leave some of it up to you guys to figure out, but the next thing I want to talk about is making this more manageable, okay? Many different ways we can do this. First of all, when you have this graph view, if we zoom out here, see how when I click on one of the nodes, it colors the top bar gray? Well, if I hold Control and click on other nodes, I'm going to choose this whole column here on the left. Now I've got these all highlighted. You can see here this loop here. You've got this furthest left loop. And it encompasses just these nodes here. The ones above it aren't related. The ones to the right aren't related. There are no flows between the bottom part of this and any other nodes. And the only other node, the head node here, connects all these other ones to the rest of the function. So with those selected, in the upper left, I can hit set node color and just choose the upper left one because I know it's not used for debugging, and that's not used to show you the instruction pointer. So they're all colored. Now with them still selected, probably should point out that if you want to color them without using that little thing in the upper left, under Edit, Other, you can do color instruction. But the other way is much more straightforward. Okay. So the other thing you can do is you can, with all these nodes selected still, I'm going to right-click, I'm going to say Group Nodes. It's the first option when you click on any node, assuming that multiple nodes are connected. And I'm going to say Last. So this box here is just asking for some text to display for this group. Okay, it can be a name or whatever. It can be some sort of information describing what it does, what that group of nodes does. But what this allows me to do is once I click OK, it's going to collapse everything all into a single node. And you can see it got stuck up in the tree here. You zoom in. It's got this uncollapsed group now. I can edit group text. So if I click uncollapse, and if you're falling behind here, I can help you out when we continue this, but go with me here. So once again, let's find another group of nodes to block here. So we've got all these loops, right?
That wasn't clear.
What we're trying to do is isolate blocks that are directly related to each other through a loop. Okay. So if we come all the way to the right here, if I just hover over this loop edge, if you look, it goes into this node here, and then if it succeeds, if this branch succeeds, it goes over here. If it fails, it goes over to the right here, which only goes into this node, which then comes back up to here. So these three nodes all belong to a single loop. So I'm going to select them again, click on the first one, hold Control, and click on the next one. Continue to hold Control, click on the next one. Right-click on the top node. And then with this list of options here, we're going to choose Group Nodes. And I'm going to say rightmost. Okay, so what we've done here is we've just begun to make this thing look a little less complicated. Still looks like a mess, but as you do this over and over again, eventually what we'll see is something much less complicated.
Hey Matthew, once we expand the nodes, how do we minimize them again?
Okay, good question. So we've got the expanded group here. You can see in each one of the blocks in here, as long as you're in when you're grouped items, you'll see this collapse group. If you click on that, that'll collapse it down. And if you want it uncollapsed, once again, click this uncollapse button here. Do I see that? there you have it. So, this is definitely a lab where along the way I'm going to check in progress, and we might spill into tomorrow, but this is hack away at this until the end of the day, and I'll be around to answer questions.